If we were making a kid's cartoon that asks the question, function, function, what's your function? The answer so far would be pretty simple. Functions help us separate parts of our code, providing a break between different ideas. And functions let us avoid having to think about the code for a problem we've already solved. In short, a function's function is to separate ideas and avoid old details. But now, we're going to look a little deeper at functions and their parameters to consider what's called overloading a function. And we're going to look at different ways to pass parameters. All of this will open up a lot more options than the basic version that we've seen so far for how to write a function. These additional ideas about functions are also going to give us a chance to learn about some new number types like double and the use of what's called a reference. So let's imagine a couple of things that we might want to do with functions that we haven't actually learned how to do yet. First, how would we handle cases where functions have different parameters? For example, we might have a function where sometimes we want to give just a first name, and other times both a first and last name. Now we've seen cases where we call functions this way. For example, we can open a file either by just specifying the file name, or by also specifying how it will be used. Or, what if we want to modify some big piece of data? For example, maybe we have a really large string containing an entire book's worth of text, and we want to substitute one word for another throughout the entire book. We'll take a look at these examples and some others as we go through this lesson. Now, just as a quick refresher review, let's remind ourselves how we create and use functions. Remember that we have to define a function by giving a function header and body, and then we can call the function. So let's say that we want to create a function that returns the average of 3 numbers. How might we write that function? Well, our function is going to return a number, the average, so we'll give it a return type of float. We'll pick a simple name like average for the function, and we'll take in 3 numbers as parameters. In this case, I've named them A, B, and C, and made them all floats, since an integer can be converted to a float without losing information, but not vice versa. So, our header is just float average, parenthesis, float A, comma, float B, comma, float C, close parenthesis. The body of the function will just add the 3 parameters together and divide by 3. So we can do this calculation right in the return statement. We'll write return, and then in parentheses, A plus B plus C, all divided by 3. We now have a function that we can call from the main function, and it works like expected. Now, what if we want to modify our function? What if we really wanted the average of just 2 numbers, or we wanted to handle averages of 4 numbers? Well, we can just create 2 new functions, each with the same name, average, but with different numbers of parameters. This approach is called overloading a function, creating more than one implementation with the same name. We'll create a version of average that has just 2 parameters, A and B. Everything is basically the same. We just return the sum of the 2 parameters divided by 2. We'll also create a version of average that has 4 parameters, A through D. And again, the function is basically the same with just one more parameter, and the average computing the sum of 4 parameters divided by 4. When we call average, we can then call it with either 2, 3, or 4 parameters. And the compiler will know to call the appropriate function, whether it's the one with 2, 3, or 4 parameters. Notice that when we overload a function, it's because it makes sense to use the same name for all the variations. We don't want to overload functions when the different variations will do very different things. But in a case like this, we want to have the average value, regardless of whether there are 2, 3, or 4 parameters. It makes more sense to call all of these functions average rather than to have a different name for each one. The function's header defines the function's signature. The signature is the name of the function, but in a more specific sense that also specifies the number and types of parameters that the function by that name will take in. When there's a call to a function, the compiler will match the call up to the same function signature, the one that has the right name, the right number of parameters, and the right types of parameters. The names of the parameters don't matter in the signature. It's just their number and types. In our previous example, we have a function named average that takes 2 floating point parameters, another function named average that takes 3 floating point parameters, and another function named average that takes 4 floating point parameters. These function implementations are all distinct from each other. And that's a rule about function signatures. No two functions are allowed to have the same signature. The compiler needs to be able to distinguish between functions, so there can't be two that have the same signature. Now, while the signature indicates the function name and the number and types of parameters, the signature does not include the return type. So, we can't overload by having two functions of the same name just returning different types, say one returning a string and one returning a float. That's not possible. However, we can convert from one type to another when a function is called. If we call a function with parameters that don't exactly match the signature, but they can be automatically converted to ones that match the signature, like converting ints to floats, then the conversion is automatic. That only works if there's just one possible matching signature, though. Let's look at one more variation. In this case, we have our original average function that takes in 2 floats. We also create another version that takes in 2 integers, and it returns an integer instead of a float. In this case, we'll perform integer division in the interior. Since the parameters are integers and we divide by 2, not 2.0, we'll have an integer result. Now, if we call the function with 2 integers, the compiler will match it up with the function's signature that has 2 integers. Since this is an exact match, that's the function that it will use. There won't be any ambiguity since there's nothing that needs to be converted. So, in this case, a call with 2 integers like 10 and 35 gives an integer result 22 rather than the floating point result of 22.5. Now I want to digress a little bit and say something about variable types in C++ that hasn't been important until now, but that we can start encountering. In particular, there are a few variations on int and float, the basic number types, and we've reached a point where it can be useful to know what they are. This goes back to how variables are defined by the computer, where each variable is a way to interpret some bits in memory, a group of ones and zeros that get interpreted to mean an integer or a floating point number or whatever. Well, each variable also has some size of memory that it's taking up. In the diagram here, you might have one variable that takes up 8 bits and a different one that takes up 16 bits. In C++, we can actually specify to a degree how many bits are used to represent numbers. The more bits that are used, the larger the number that can be represented. For integers, that means that we can represent larger integers. For floating point numbers, that means that we can use more digits of precision, and we can represent both much larger and much smaller numbers. Just to give an idea, an 8-bit integer can represent 256 different numbers. A 32-bit integer can represent around 4 billion numbers. For integers, we have several options. These range from the char, a single character that's actually stored as an integer, all the way up to a long int. Now the exact sizes of integers aren't specified, but we do know that a long int has at least as many bits as a long int, which has at least as many as an int, and so on. Choosing larger integers lets you represent larger numbers, but at the cost of more memory to store values. And similarly, floats have a longer version, the double, and an even longer version, the long double. The thing to remember when passing parameters is that these different types are actually different. And that means that if you have a function expecting one type, and you call it with a different type, it often needs to perform a type conversion in order to match the call to a specific signature. And some of these type conversions can be very tricky. Take a look at this code. This is the same program we saw earlier, but now we're calling it with 10.0 and 35.0 rather than 10 and 35. And you might think, oh, that's two floating point values, so obviously it'll correspond to the function definition that takes two floats. Now, while some compilers might guess that, you'll probably find that you get a compiler error when you compile this code, saying that we're trying to make a call to a function named average, and we're giving two doubles as parameters. The compiler can't figure out if it's better to convert those to floats and use the float version, or to convert those to ints and use the int version of average. It's ambiguous what's wanted, so it won't compile the program. So even though we thought we had called with floats, floating point literals are treated as doubles by default. Now, one way to get around this is to make sure you call with floating point numbers. Anytime we write a floating point literal, we can append an f onto the number, and that indicates that the number should be treated as a float. And now, this code will compile and run just fine. There are similar methods for other types. For instance, adding a double LL after a number ensures that it's treated as a long int. So, if there's any ambiguity in terms of how a function might be called, you need to be careful. If you choose to overload a function definition, make sure you know how you're calling it. You need to have the types of the parameters specified correctly in the signature, and you need to have your arguments for those parameters specified correctly in the call. There's one more way that we can provide functions with the same name, but different parameter sets. We can specify a default value for one or more of the parameters. If, when the function is called, the corresponding argument is left out of the call, we use the default parameter value instead. To do this, we just set an initializing value for the appropriate parameter, assigning it to some value inside the parentheses. When it's done this way, the assignment is understood by the compiler as one to be used if the corresponding parameter is not provided. Let's see an example. Say that we want to create a function to print out a string multiple times. Let's call it printMultiple. We can let printMultiple take in the string to print and the number of times to print it. There's nothing to return. That is, the function does not need to return a value to the place it was called from, so we'll have a void return type. Now, if someone doesn't specify how many times to print the string, we might choose to have a default number, like 1. If so, our header would look something like this: void printMultiple, open parenthesis, string s, comma, int times equals 1, close parenthesis. So there are two parameters, a string called s that we're taking in, and an int called times, the number of times to print, which has a default value of 1. If we call the function with both parameters, something like hello and 5, we'll get the string printed out 5 times. Hello, 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 hello. On the other hand, if we call it with just a string parameter, like world, then times has the default value, so the string is printed out just once. If there are multiple default parameters, then arguments from the function call are assigned to parameters left to right. That is, the first assignment, the first argument, goes to the first parameter. The second argument gets assigned to the second parameter, and so forth. You can't have some parameter in the middle be assigned a default value. Once one is assigned, everything after it must also be default. Let's look at an example. Here we have a very simple function, printPair, created for illustration. It takes in 2 integer parameters and it prints them out with a space in between. The first parameter has a default value of 1, the second a default value of 2. If we call the function with 2 arguments, like 10 and 20, we get 10 space 20 printed out. If we call the function with no arguments, we get 1 space 2 printed out. Each of the parameters took on its default value. If we call the function with one argument, 10, then what's going to happen? Well, the argument 10 will be assigned to the first parameter. The second parameter will use its default value. So what's printed out is 10 space 2. Default parameters are commonly used to control how a function works when there's a normal or common way to do something set as the default. But you want to let the programmer have the option of selecting some other behavior if needed. Setting default parameters is an alternative to overloading a function by specifying different signatures. Overall, overloading functions is a useful way to tie similar functionality together with the same name. But keep in mind that there always needs to be an unambiguous way to determine which definition corresponds to every call. Okay, we're going to shift topics to a new way of dealing with parameters in a function using something called references. What this does is allows us to share information without making needless copies. To see what I mean, imagine if someone asked to borrow a book or some other document from you. Now, the way you respond might depend on how that person would treat the book. You've got a few ways you can respond. On one hand, you could just let them borrow the book, and they might make changes to it, and you might be okay with that if they do. In fact, maybe you want them to make those changes, highlighting key parts or fixing mistakes and so on. Another option is that you could let them borrow it, but only if they promise to just look at it, to not make any changes to the book itself. Or third, maybe they want to mark it up, they want to be able to write things in it or tear out pages or whatever else, but you don't want them to make any changes to your book. So in that case, you might make a photocopy. Let's pretend there's no copyright issues. It turns out that those three options are exactly our options for how we handle data. Up to this point, we've really only seen the third option. When someone else wants the data, we make a copy of it. Then they use that copy. This happens when we assign variables. Saying A gets B means that we make a copy of B and assign it to A. And it happens when we pass data in parameters. The arguments are copied into the parameters in the function. We can then mess around with that new data stored in the new variable, or that's within the function, all that we want, and it never affects the original. But it turns out that we can also handle data in those other two ways. We can let the original data be used with permission to modify. Or the original data can be used but with no permission to modify. We can allow either of these kinds of access to our original data with something called a reference. I'll start by showing how a reference works in general, but the place where it's used the vast majority of the time is in a function header. A reference is a way of describing a particular variable. Now normally, when we define a variable, it gets its own box of memory. And if we do something to that box of memory, like assign a value to it, it's not going to affect any other box. With a reference, though, we don't create a new box of memory for the variable. Instead, we use an existing box of memory, and we say that the variable refers to that box of memory. Basically, our variable becomes another name for some box of memory that already exists. So, anything we do to that new variable must affect the original box of memory also. The way we specify a reference is by putting an ampersand symbol after the type when we first declare it. For example, int ampersand. We have to initialize our new variable to refer to some other variable. So here's an example. First, we create a variable a that we initialize to the value 1. Next comes our reference. We're going to create a variable b that is a reference to an integer. So we write int ampersand b. And we have to make this a reference to something. We can't just leave it there. So we initialize this to a. And what this means is that b is going to refer to the exact same box of memory as a. When we print out the values of a and b, both of them show up as 1. And we can assign a new value, 2, to a. And when we do so, this changes the value stored in that box of memory. So when we print out both a and b now, both of them show up as 2. The same thing happens if we assign a new value 3 to b. The box of memory that B refers to has its value changed to 3. So, printing out the values of A and B now indicates that both have the value 3. Essentially, A and B are referring to the exact same thing. It's like sharing your book. Whatever that person does to it affects your book. You both have the same book. It's not that the borrower has a separate copy. But the most common way that references are used is when calling functions. And that's because we can declare any of the parameters in a function to be a reference. And that means that the parameter will not be a copy of the argument that comes in. It'll be a reference to the argument that comes in. So any changes to the reference parameter will be like a change to the original. The term we use to describe this is passing by reference. And that's distinguished from what we've been doing before, which is called passing by value. When we pass by value, we're copying the value of the argument into the new box of memory set up for the parameter. When we pass by reference, we don't copy anything. We just let the parameter refer back to a shared version of the input. So let's see how passing by reference works. Say that we have a savings account balance and we'd like to increase the balance by some percentage to account for earning interest. We can create a function named increasePercentage that will take two parameters. The first one will be the value that we want to increase, and the second one will be the percentage to increase by. Now, the key thing here is that we're going to modify the balance. So the first parameter needs to be a reference, not just a basic parameter. So we'll write float ampersand followed by value for the first parameter. So when the function is called with arguments savings balance and 10, the first argument, savings balance, is passed by reference. In the function's memory, the parameter value just refers to the exact same block of memory as savings balance from the main function. The second argument, 10, is passed by value. So a new box of memory, named percentage, is created in the function's memory area, and 10 is copied into there. Thus, when we modify the variable named value in the function, it's actually modifying the same box of memory as savings balance in the main function. After the function returns, we'll find that the value in savings balance has in fact been changed. Okay, let's practice this. Going back to one of our motivating examples, say that we have a really long string, and we want to do a search and replace for some word in the string, finding every occurrence of that word and replacing it with a different word. Now don't worry about the body of the function, but can you come up with a header for a function that will modify the string in that way? Okay, here's what the header could look like. A search and replace function doesn't need to return anything, so it can have a void return type. And the name can be something descriptive like search and replace. The order of parameters is up to you, but in my example, the long string to modify will come first. So we would write this as string ampersand main underscore string, where main underscore string is going to be the parameter. Then we have two more string parameters, one being the word defined and the other being the replacement. Now these don't have to change, so they can be regular parameters without an ampersand, and thus are set by passing by value. Inside that function, we could modify main string to change the main string, and that would change the string that was in the first argument position. In the function call, notice that we have a string variable in that first position, followed by two more strings. So, passing by reference makes it possible to modify a value. It also has the advantage of not having to go through the process of copying the variable. Now, copying is not a big deal in most cases, but if the variable is something really large, like say an entire video file, we don't want to take the computational time and memory of going through and copying it. Think back to the book borrowing example. If we could avoid making a photocopy of the book, wouldn't that be better? The ability to not have to copy information needlessly is an advantage, so why wouldn't we always want to do that? Why wouldn't we just always pass by reference? Well, there's two main reasons. One, is if we know that we want to modify the parameter in our function, but we don't want it affected back in the main program. So we'd like the function to be as disconnected from where it was called as possible, so that we don't want to needlessly tie things together that shouldn't be. Passing by value is the right solution when we want our function to be as much of a black box as possible, since we need to make a copy of the data regardless. The other reason for passing by value is a little more subtle. If we pass by reference, then the argument that we call with needs to be a variable. It can't be a literal. So look at this modification of the previous program. Now, instead of the first argument being a string variable, I've tried to pass in a string literal. This will give a compiler error. We can't have a string literal since there's no box of memory to refer to. So, when we pass by reference, we have to give variable arguments. That said, there is a workaround that lets us pass a literal by reference after all. And the trick here is to add the word const in front of the reference parameter. Adding the keyword const tells the compiler, we don't need to copy this data, and we promise that we won't modify it. It will stay constant. We call this passing by const reference. Thinking back to the book analogy, this is like loaning your book when the person has promised not to do anything to it. We didn't have to make a photocopy, but no one's allowed to modify it. Now this code is an example. Notice that our first parameter is now const string ampersand main string. This lets us use any parameter there. We can pass in a literal now, since we've promised that it won't change. There's no reason that we'll need to modify the memory location, and in fact we're not allowed to modify it. We can't assign a new value to main string, or change a character, or do anything. It must remain constant. In fact, if our function is still supposed to search and replace, we'll have to do something like return a string, since we can't modify the parameter anymore. We'll see const again in object-oriented programming, but for now, I want to demonstrate one other way that const can be used. This is actually one of the oldest uses of const, going back to plain old C. If we ever have a variable that we want to assign a value to, and we know that value will never change, we can declare it to be a const variable when we first declare and initialize it. We just write const in front of the type, and now we have a variable that will never change. For example, I might have a variable named pi, and initialize it to a specific value, and then use that value everywhere. Declaring a variable to be constant makes sure that the intent of the variable as an unchanging value is maintained. Now the use of pass by reference has one other nice benefit besides letting us modify an individual parameter. It's also a way of, in effect, returning more than one value. Ordinarily, a function can only have one return type. But if we have multiple parameters that are passed by reference, we can use that to modify the values of each of them. And so in this way, a function can, in effect, return multiple values by modifying multiple arguments. Let's see one last example. Here we have a function that we use to convert a number of days to a number of weeks and a number of days. There are three parameters. The first one is the total number of days, passed in by value. The second and third are the values that we want to return, the number of weeks and the remaining days that is equivalent to. Inside the function, we can set values for the second and third parameters. When we call the function, we pass in the number of days that we want, along with variables to hold the two values to be returned. And this works. The variables are passed by reference, so their values are set by the function. We've effectively returned two values with one function call. We'll be writing functions throughout the remainder of this course, and we'll continue to gain experience in learning when to overload functions, when to pass by value, and when to pass by reference. A good rule of thumb is to use pass by value as a default, unless you have a good reason not to. That way you're less likely to have errors or run into problems. But there are lots of good reasons to use pass by reference and pass by const reference. Pass by reference lets us modify parameters, and in effect return multiple parameters. And pass by const reference lets us avoid unnecessary copying and can help optimize code when we're dealing with large data. In the next lecture, we'll be looking at ways of finding and handling errors that we encounter when working with functions. See you then.